Welcome to a lesson with Dr. Powell. Okay, ready for some fun equations for torsion and kappa curvature that make our computations really nice. Okay, so these formulas work off of r prime, r double prime, and r triple prime. In other words, the velocity vector, the acceleration vector, and you could say the jerk vector. So if you can compute these, you're good to go. And then it's just some dot and crossing after that, and that's about it. And then we can get these. So how does this work is what we're going to go over now. Okay, for starters, remember how we wrote the acceleration vector in terms of a t and an n component. So r double prime is the acceleration vector. So let's write that out. So r double prime was simply equal to s double prime t plus s prime squared kappa n. So we mentioned this in our earlier video. We weren't using it then, but we'll use this idea right now. Okay, so that's what r double prime is. Now, what is r prime? R prime, we could think of as, let's write it in terms of t. That would simply be s prime, which is the length of the velocity vector. And so it's s prime times t, which is because the velocity vector is in the direction of t. So that's what r prime is. Now, if you take a look at this, what would happen if we took r prime cross r double prime? Notice that it's going to distribute. This is going to distribute in, and t cross t is going to be 0. So you can just ignore this part when it crosses in and just go straight to here, which is very nice. So what we end up getting, we have an s prime times an s prime squared to give us an s, because this is not in the vector, it's just a scalar multiplied to it. Of course, it's a function of t though. So we're going to get s prime cubed and then kappa and then t cross n, which is just b, which is great. So if we wanted to find kappa, actually, what if we were to take the absolute value of this, or the length of this, okay, the length of this thing, of this vector, then the length of b is just 1. So really the length here is just equal to s prime cubed kappa. And then what if we were to divide this by s prime cubed, then you'd actually get kappa. So we have a nice formula for kappa if we just rewrite this a little bit. Remember that that s prime is nothing more than r prime, the length of r prime. So the length of r prime is equal to s prime. And so we just take that and cube it, and look, we have a wonderful formula right here for curvature. Okay, now what about for torsion? Let's get there. We're going to look at the part of the jerk, r triple prime, that's going to be parallel to b. There's a reason for that, and we'll get to that. But for now, let's just try to focus on what that is. What is the part of this, or the component of this in the b direction, or the projection of r triple prime onto the vector b? So that's all we need. We just need to know what the projection of r triple prime is onto b. And actually, that's not too hard to figure out from what we have already. Once we get that, what we'll actually do is we're going to be dotting this r triple prime with this cross product right here. And when we cross it, so everything that's not in the projection that's orthogonal, it would just vanish in the cross product. So really all we need is just what's in the direction of b, and we're going to ignore things that are orthogonal to that. And that'll actually allow us to take this, the dot product of this r triple prime, and this cross product, and you'll see how the torsion pops out very nicely. So first, we got to figure out what that projection is. R triple prime on into the direction B, and we're going to ignore anything that's orthogonal. Okay, so let's go to that point, see what we can do with that. All right, so well, we're going to start here with this R double prime and just take the derivative of this. Now in doing that, let's not take the whole derivative though. Let's just try to ignore parts that we know won't benefit us. Okay, for instance, right here, we're going to have to use a product rule, but when we do that, we're going to bounce around with having t and t prime, and t prime, that's like the directions of t and n, which are orthogonal to b. So actually, we're going to ignore this and not even take care of this product rule. We're just going to go to the next one because it's not going to give us anything for the projection. So let's go to the next one and take a derivative over here. Now we're going to have two parts. We're going to have n and n prime. Now the part that's n is orthogonal to b, so we can ignore that. So the only thing we really need is just n itself. Now it's just n itself, and so we end up getting just simply so the part of the product rule that we want from this will have an n prime in it. Okay, okay, so we'll look at that, and s prime squared kappa. So that's kind of the part that we're looking at here. In fact, if we rewrite this as dn dt, and let's just freely divide by s prime and multiply by s prime, and so kappa s prime squared. Now the reason why we do that is because the thing about s prime as being the absolute value of v, this actually turns into dn ds. And then we have kappa, and we have s prime cubed. This allows us to use one of our formulas for Net-Surret formulas, dn ds. We can rewrite this as negative kappa t plus tau b. Now we take that, and okay, so basically we have this. Now notice when we do that, and we're only looking at things in the direction of b, because our main goal is to be able to dot this with this, and this is in the direction of b. Notice that this part doesn't matter, and we're just left with s prime cubed kappa times tau b, and if we dot it with this, b dot b will be 1, the unit length, and we end up getting s prime cubed times s prime cubed, okay, times kappa, so basically just that squared times tau. So when we take a dot product, we just end up getting this this right here, which, remember that s prime cubed kappa, the s prime cubed kappa is the same thing as r prime cross r double prime. So to get tau, what it all just amounts to doing the following. We take r triple prime, we dot it with r prime cross r double prime, and then we divide it by the length of this, which is just, so if you take the length of b is just 1, so it's just s prime quantity cubed kappa, or which maybe we'll rewrite that, because we're not going to compute that actually, right? We're going to compute the length of this, so we just compute that and compute its length. So the length of r prime cross r double prime. And honestly, we just then, to get tau, since we're taking in this projection, let's see, this is just a dot product here, right? Oh, that's perfect. That dot product is just a number. So so basically you just take the dot product of this and that cross product and divide it by this squared, right? Because we had to square it. And that's actually equal to torsion right there. So all we have to do is compute our prime, our double prime, and our triple prime, take the dot product of this with that cross product, and then just divide by this cross product squared. Poof, we get torsion. Thanks for watching.